Good morning, students. Myself, KK Leka, Assistant Professor in Biomedical Engineering Department in Erode Engineering College. In today's class, we are going to see about biofluid mechanics in biomechanics. First of all, we have to know what is biomechanics. Biomechanics is the study of the structure and function and motion of the mechanical aspects of biological systems at any level, from whole organism to organs, cells and cell organelles, using the method of mechanics. Biomechanics is a branch of biophysics. It involves the principles of anatomy and physics in the description and analysis of a movement. The study of biological structure, processes, and functions by applying the methods and principles of mechanics is known as biomechanics. The purpose of studying biomechanics is to understand the forces acting on the human body and also to manipulate these forces in treatment procedures so that human performance may be improved and further injury may be prevented. Okay, why we are studying biomechanics? For better understanding of both joint function and dysfunctions. Design improvements in devices, example, joint arthroplasty systems and orthotic devices, to understand how the musculoskeletal system functions. Useful in patient evaluations and treatments. Important for clinicians such as orthopedic surgeons and physical and occupational therapists. Okay, let's go into the biofluid mechanics. Biofluid mechanics is a course that covers the dynamics of fluid flow in human physiological system. In engineering principles, the fluid dynamics concepts will taught the context of cardiovascular systems. Why we are using biofluid mechanics? It plays a major role in cardiovascular system. It is important to understand the forces and movement of blood cells and whole blood, as well as the interaction between blood cells and the vessel wall. Okay, what is fluid mechanics? First, mechanics is the application of laws of force and motion. Well, fluid mechanics is the application of laws of force and motion in fluids. There are two branches of fluid mechanics. Fluid statics or hydrostatics is the study of fluids at rest. The main equation required for this is Newton's second law for non-accelerating bodies. In fluid dynamics, it is a study of fluids in motion. The main equation required for this is Newton's second law for accelerating fluid. Well, biofluid is the biological fluid that can be excreted, secreted, obtained with a needle or developed as a result of pathologic process. Biofluid mechanics is the focused on how biological systems interact with and or use liquids and gases. For humans, this includes obtaining and transporting oxygen blood, maintaining body temperature and regulating homeostasis. A fluid is a substance which deforms continuously under the application of shear stress. Some define a fluid as any material that takes shape of the container in which it is held. The fluid is either a liquid or a gas, for example, blood, water, air and oil. Normal fluids in our bodies are bloods. Major is bloods. Blood plays a major role in body defense against infections by carrying waste away from our cells and flushing them out of the body in urine, feces and sweats. And other fluids are saliva, semen, vaginal fluids, mucus, urine, etc. Okay. CS stress. CS stress is defined as a force per unit area acting on the surface element. Stresses have both magnitude and direction, and the direction is relative to the surface on which the stress acts. There are normal stresses and tangential stresses. Pressure is the example of normal stress and act inward toward the surface and perpendicular to the surface. The shear stress is example of tangential stress. That is, it acts along the surface parallel to the surface. These are the diagrams that explains the shear stress and normal stress. If the force acting in the all of the sides means the stress is known as confining stress, which means the stress is equal from all the directions. The second is tensional stress. It is the compression feel like stress. Next is compressional stress. The force is acting in the both sides, both two sides, that compresses the element. In shear stress, the stress applied in upward and downward area in opposite directions. The area and force applied is that forms the equations. Shear stress tau is equal to force by area. If you are considering fluid as a continuum, we can suppose that there are no inhomogeneities within the smallest division of fluid that are made. These excretes properties such as viscosity, density, temperature, among others, must be constant throughout the entire fluid. In most engineering applications, the average or macroscopic effects of large number of molecules is considered. We thus do not concern about the behavior of individual molecules. The individual molecules are does not consider in this. The whole element, that means the whole fluid such as blood, are considered. The fluid is treated as an infinitely divisible substance, a continuum at which the properties of the fluid are considered as a continuous function of the space variables and time, such as smooth functions of the fluids. The properties of fluids are density, viscosity, stress. These properties are explained in the below. First is density. Density is the mass per unit volume of the fluid. In other words, it is the ratio between the mass and volume of the fluid. Density is denoted as the symbol rho. Its unit is kilogram per meter squared. Density rho is equal to mass per volume kilogram per meter cube. Density offers a convenient means of obtaining the mass of body from its volume or vice versa. The mass is equal to the volume multiplied by density. It is simply explained how tightly or loosely packed a substance is, or the number of things or people in a certain area. Next term is viscosity. Viscosity is the quantity that describes a fluid resistance to flow. Fluid resists the relative motion of immersed objects through them, as well as to the motion of the layer with differentiating velocities within them. Viscosity describes the internal friction of moving fluid. The fluid large viscosity resists motions. Some examples of viscosity in our daily life are honey, engine oil, brake oil, lubricants, cooking oils, liquid soaps, printing inks, super glues, etc. Viscosity denotes the opposition to flow. The Newton's law of viscosity tau directly proportional to du by dy. Tau is equal to mu du by dy, where mu represents the viscosity and tau represents shear stress, which is force by area. Du by dy are rate of shear deformations. There are actually two quantities that are called viscosity. The quantity defined above is sometimes called dynamic viscosity, absolute viscosity, or simple viscosity to distinguish it from the other quantity, but is usually just called viscosity. The other quantity is called kinematic viscosity. The SI unit of viscosity is the Pascal second. Kinematic viscosity is the inherent resistance of fluid to flow when no external force is exerted except gravity. It is the ratio of dynamic viscosity to its density, a force-independent quantity. Kinematic viscosity can be obtained by dividing the absolute viscosity of the fluid with the fluid mass density. Kinematic viscosity is the measure of fluid's internal resistance to flow under the gravitational force. It is determined by the measuring the time in seconds required for fixed volume of fluid to flow a known distance by gravity through capillary within a calibrated viscometer at a closely controlled temperature. Kinematic viscosity is equal to dynamic viscosity divided by fluid mass density. V is equal to rho eta by rho. We have V is kinematic viscosity, rho is fluid density, eta is dynamic viscosity. The SI unit of kinematic viscosity is the square meter per second, meter square per second. If you are dividing the absolute viscosity of the fluid with the fluid mass density, which results in kinematic viscosity. The next is pressure. Pressure is the pressure of the fluid is the force per unit area of the fluid. In other words, the ratio of the force on a fluid to the area of the fluid held perpendicular to the direction of the force. The continuous physical force exerted on or against an object by something in contact with it is known as pressure. A simple example for pressure is holding a knife to a piece of fruit is a simple example for pressure. Pressure of depth h is in the figure shows is how pressure is applied in upward directions. Pressure at depth h p is equal to rho gh. There are two types of pressures, absolute pressures and gauge pressures. The absolute pressure is when the pressure is measured relative to a perfect vacuum. The vacuum pressure is known as absolute pressure. It is a pressure that is relative to a zero pressure in empty air-free space of the universe. In simple words, we can explain total pressure at a unit point in a fluid equaling the sum of gauge and atmospheric pressure is known as absolute pressure. In gauge pressure, when the pressure is measured relative to the atmospheric pressure is known as gauge pressure. It is the pressure of the system above atmospheric pressure. The gauge pressure is mainly used to measure the pressure difference between a system and its surrounding atmosphere. The gauge pressure is equal to absolute pressure minus absolute pressure in atmospheric. If you are adding gauge pressure and atmospheric pressure, it is known which results in absolute pressure. Temperature. It is the property that determines the degree of hotness or coldness or the level of heat intensity of the fluid. In simple words, it is a physical quantity that express the degree of heatness or coldness. Expressed in terms of any several arbitrary scales and indicating the direction in which heat energy is produced. Next is specific volume. Specific volume is the fluid occupied per unit mass. Volume of the fluid occupied per unit mass. It is the reciprocal density. Specific volume is a property of material defined as the number of cubic meters occupied by a kilogram at a particular distance. Specific volume is denoted by the symbol V. Its unit is meter cube per kg. Specific volume V is equal to V by M, meter cube by kg. It is calculated the volume and mass. Specific volume equals to volume divided by mass. Volume is measured in cubic meter and mass is measured in kilogram. The examples of specific volumes are waters, salt water, mercury. The water contains 0.00 100 meter cube per kg specific volume. In salt water, it has 0.00097 meter cube per kg specific volumes. The main difference between the volume and specific volumes are extensive properties. It's extensive properties. The volume is extensive property, whereas specific volume is intensive property. Next is specific weight. Specific weight is the weight possessed by a unit volume of a fluid. It is denoted by W. Its unit is Newton per meter cube. If we are calculating the specific weight by multiplying the density by the acceleration of gravity, which is 9.81. To calculate specific weight, W is equal to weight divided by volume, Newton per meter cube. The difference between density and specific weight is, while the density measures the mass per unit volume of the liquid, when the specific gravity is used for measuring the relative density. Next is specific gravity. It is the ratio of the specific weight of the given fluid to the specific weight of the standard fluid. It is denoted by the letter S. It has no units. The ratio of the density of the substance, typically a liquid or a solid, compared to the density of the water. Water is a density of 1.0 g by cc at a normal pressure and temperature. So the specific gravity of the substance, that is 1.6 times heavier than a water, would be equal to 1.6. Specific gravity S is equal to specific weight of the given fluid and divided by specific weight of the standard fluid. In simple words, the specific gravity is defined as the ratio of the density of the given substance to the density of the water. Standard fluid is our water, H2O. The next is fluid statistics. Fluid statistics are also known as fluid hydrostatistics. It is a branch of fluid mechanics that studies fluid at rest and the pressure in a fluid or exerted the fluid on an immersed body. Newton's second law of motion, simplified to the sum of the force acting on the fluid is equal to 0, is the primary governing equation that is used to solve fluid statistic problems. The primary quantity of interest within the fluid statistic problem is the pressure field throughout the fluid. No acceleration and density is constant. The fluid statistic is the branch of fluid mechanics that studies incompressible fluids at rest. It encompasses the study of conditions under which fluid at rest in stable equilibrium as opposed to fluid dynamics. The study of fluid in motion. Liquids and gases are the both fluid. The examples of fluid statistics are when you are drink using a straw. It is a good example for fluid statistics. You reduce the pressure at the top of the straw and the atmosphere pushes the liquid up the straw and into your mouth. pressure variation in a static fluid. This equation indicates that the pressure difference between 2 points in static incompressible fluid can be determined by the measuring the elevation difference between 2 points. Devices used for this purpose is called manometer. P minus P naught is equal to del B is equal to rho GH, where the pressure difference we are differentiating the two different pressures, that is known as the pressure variation in static fluids. At P naught is the reference level at pressure and P is the greater than P naught, that is location and pressure of the interest. Next is buoyancy. Buoyancy is defined as the net vertical force acting on an object that is either floating on a fluid surface or immersed within the fluid, that is Archimedes' principles. To determine the net force acting on the immersed or floating object, the same relationship for the pressure variation within the static fluids. In buoyant force, some objects are floating, some objects are sink. Why we are studying fluid mechanics, fluid statistics is to understand the behavior of fluid under various forces at a different atmospheric conditions. The application of fluid statistics are pressure measurement with hydrostatic floating or submerged bodies, water dams and gates, liquid storage tanks. The properties of fluids are density, temperature, internal energy, pressure, specific volume and specific weight. The buoyant force is equal to density of liquid into gravitational acceleration into volume of fluid is equal to density into gravitational acceleration into height of fluid into surface area of the object. F is equal to rho GV. Rho we can explain in another terms, rho GHA. F is the buoyant force of the liquid acting on the object. When rho is the density of the liquid, which is measured in kilogram per meter. When G is the gravitational acceleration, which is usually 9.80 meter per second. Where V defines the volume of the liquid displaced. M or liters, where 1 m is equal to 1000 liters. H is the height of the water displaced by floating objects. A is the surface area of the floating object. Okay, next we are going into the type of fluids. The first type of fluid is ideal fluid. It is a fluid which cannot be compressed and have no viscosity, falls into the category of ideal fluid. Ideal fluid is not found in actual practice, but it is an imaginary fluid because all the fluid that exists in the environment have some viscosity. There is no ideal fluid in reality. It is a fluid that incompressible and no internal resistance to flow, zero viscosity. The examples are ideal fluid are a fluid which is incompressible and has no viscosity falls in the category of ideal fluid. Actually, all the fluid existing or present in the environment are called real fluid. Some of its examples are petrol, air, etc. In real fluid, the fluid which has at at least some viscosity is called real fluid. Actually, all the fluids existing or present in the environment are called real fluid. For example, water. The fluids that have viscosity and their motion is known as viscous flow. Next is Newtonian fluid. If a real fluid obeys the Newtonian law of viscosity, is known as Newtonian fluid. The shear stress is directly proportional to the shear strain, that is known as Newtonian fluid. Examples are water, oil, gasoline, alcohol. Newtonian fluid is defined as one with constant viscosity with zero shear rate at zero shear stress, that is the shear rate is directly proportional to shear stress. Non-Newtonian fluid. The non-Newtonian fluid is a real fluid, does not obey the Newton's law of viscosity, that is known as non-Newtonian fluid. The examples of non-Newtonian fluids are blood, yogurt, ketchups, gels, and alcohol. Alcohols are examples of Newtonian fluid. Soap solution, toothpaste, cosmetics, butters are examples of non-Newtonian fluids. And the ideal plastic fluids. The ideal plastic fluids, some toothpastes are comes under non-Newtonian fluids, some are comes under ideal plastic fluids. The fluid having the value of shear stress more than yield value or shear stress is perpendicular to the shear strain is known as an ideal plastic fluid. Examples of ideal plastic fluid is toothpaste. In this above graph, they are explained the types of fluid, the differences between the shear stress and velocity. The first ideal fluid, ideal solid. The ideal fluid is constant increment. The ideal solid is constant straight line. The Newtonian or non-Newtonian fluids are when velocity increases, the stress is increased gradually in Newtonian fluid, but in non-Newtonian fluids, that's in some point they are increasing, at some point it starts to decrease. Next is fluid kinematics. Kinematics is generally study of motion. Using kinematic relationship, you can describe the motion of any particles in a space and time. Kinematic is a subfield of physics developed in classical mechanics that describes the motion of points, bodies, and systems of bodies. The subdivision of classical mechanics concerned with the geometrically possible motion of the body or system of the bodies without consideration of the forces involved is known as kinematic fluids. The types of fluid flows are steady flows, unsteady flows, uniform flows, non-uniform flows. When the steady flow is in which the fluid characteristics like velocity, pressure, and density, etc. at a point do not change with time. In an unsteady state in which the fluid velocity, pressure, or density at a point changes with respect to time. The flow is not in a function of time is called steady flow. The flow in the steady state flow refers to the condition that fluid property at a point in the system do not change over time. The major difference between the steady flow and unsteady flow is there is so much derivation from the mean. The flow, the time dependent, it is time dependent, and steady flow is not time dependent. The flow through a pipe of variable diameter and constant pressure head is example for steady flow. Uniform flow. Uniform flow is the in which the velocity of at a given time does not change with respect to space. The length of direction of the flow. Fluid flowing into a different parts of the fracture surface with equal flow velocity per unit area is known as uniform flow. The non-uniform flow in which the velocity at any time changes with respect to space, changing in space. When there is a change in velocity of the flow at different points of the flowing fluid is known as, for a given time is known as uniform, non-uniform flow. The next type of flow is laminar flow. Laminar flow is in which the fluid particles move along well-defined path or streamline. It is a type of flow pattern of fluid in which all the particles are flowing in a parallel lines. In the figures shows the laminar flow. There is no mixing between the layers of flow. It flows just like parallel lines. The next type of flow is turbulent flow. In turbulent flow occurs when there is a liquid is moving fast with mixing between layers. The speed of the fluid at a point is continuously undergoing changes in both magnitude and directions. The figure shows the turbulent flow. There is a mixing between the each and every layers. The layers are merged together, mixed together. The turbulent flow is caused by excessive kinetic energy in a body in parts of the fluid flow, which overcomes the damping effect of the fluid's viscosity. The next type of fluid flow is compressible flow. The compressible flow in which the density of the fluid changes from point to point, which means the density is not constant for the fluid. It is a branch of fluid mechanics that deals with flows having significant changes in fluid density. Area of fluid mechanics that deals with fluids in which the fluid density varies significantly in response to a change in pressure. Incompressible flows. in which the density of the fluid changes from point to point. The density is constant for the fluid. Incompressible flow refers to a flow in which the density remains constant in any fluid parcel. The figure shows the difference between the compressible and incompressible flow. The first figure shows the incompressible flow. At CV1 and CV2, the flow is constant. There is no change. But in compressible flow, in CV2, it compresses the flow points depend upon the area. Next is conservation laws. Conservation of mass. The mass can neither be created nor destroyed within the volume and system of interest. In special, we can use the conservation of mass to solve various fluid mechanic problems. For example, the volume flow rate. In physics and chemistry, the law of conservation of mass or principle of mass conservation states any system closed to all transfer of matter. It is a mass is neither created nor destroyed in chemical reactions. In simple, we can explain it as no atoms are created or destroyed in chemical reactions. The above figure shows the conservation of mass. How the conservation of mass is applied in the turbulence. The volume or a volumetric flow rate Q for an incompressible flow through a non-deformable volume. The volume flow rate into the volume must be balanced by flow out of the volume. However, since the volume is non-deformable, the volume flow rate can be calculated at any one location at any time within the system. The volume flow rate Q is equal to integral V bar dA bar. The volume flow rate divided by area is defined as the average velocity at particular section of interest. The volume average is equal to Q, volume Q divided by area is equal to 1 by A integral V bar dot dA bar. Conservation of energy. It states that the law of conservation of energy, total energy of an isolated system remains constant. It is said to be conserved over time. This law means that energy can be neither be created nor destroyed, rather it can only be transformed or transformed from another. According to which the energy of interacting bodies or particles in a closed system remains constant. Thank you for watching my video.